Hey, what's up, guys? Okay, so today I'm gonna talk about is the topic called infinite products. So this topic is, I think it's important in the complex analysis or the advanced calculus analysis. But usually, but because yeah, I mean I don't know why, but usually in the calculus or advanced calculus or analysis, people usually talk about infinite sum. Okay, so you heard about like many kind of root test, ratio test, and whatever test, and whatever integral test, whatever stupid test about how to deal with in this infinite sum. But seldom people will talk about this infinite products. It's not difficult, and they are related, and I think it's important. So I think I want to make a video and connect and collect all some important factor about this infinite product so that you guys can have a reference. Okay. And I think this infinite product in the complex is much more important. So if you know this, and you can use this infinite product to prove so-called Weierstrass factorization theorem. So I would say this theorem is it's like a more advanced theorem in the complex analysis. It's not like the some simple one that you should learn if you are not math major. Okay, so definition. So the infinite product, I think, so remember how do we define the converge of this? We will use so-called partial sum. So usually people will define Sn to be as a k, maybe k from 1 to n. And if Sn converge to S, Sn goes to infinity, then we will say that this converge. Okay, so we do the same thing for infinite products. So any number I talk in this video will be complex. Okay. So when we say this approach to Z, so we will first define the partial sum. Okay, and then we will say the partial sum converge. Usually I will use P because P means for product. So PK approach to Z, K as infinity. Then this I will take say as converge. Okay, but there's a important. So there's a special case. Unless if Z is 0, then I will say PK diverge. So I will say diverge. Okay, so this is the only difference. In the infinite products, if the result is 0, I say diverge. Okay, so this is the only difference. Okay, so theorem. This is you can compare with the Cauchy. So in the Cauchy theorem, and in the standard results, right? Standard results, we know that if an converged, if a summation n from 1 to infinity converge to something, maybe a, then we know that for every epsilon greater than 0, you can find n such that when n greater than m greater than n, then you will have an, you will have the partial sum, right? You can take an plus 1, up to an less than epsilon. Okay, so this is just very simple. This is a Cauchy, right? Definition of the Cauchy sequence. So convergent sequence implies the Cauchy sequence, and the Cauchy sequence do not imply convergent sequence if the you need to the completeness of the matrix space. Okay, so we have the same thing for infinite products. Okay, so if 1 plus an, so we will always use this 1 plus a. So n from 1 infinity 1 plus an converge. If and only if for epsilon greater than 0, there is this n such that 1 plus an plus 1, 1 plus an plus 2. So it's a partial product, an minus 1 less than epsilon. Okay, so proof is similar as the Cauchy. So similar as the sum the series infinite series results. So I skip the proof. It's not difficult. You can try yourself. Okay. Okay. So a theorem. So now we start to prove some theorem related to this infinite product. Okay. So suppose if all n are greater than 0, then 1 plus an product n from 1 to infinity converge if and only if summation an converge. Okay, so this is the first theorem that related to us. Okay, so related to the infinite sum. So this I should prove. Okay, so let's prove. Let's prove. So what should we start? Okay, so okay, so let's prove these directions. Okay, and yeah. Okay, so this direction is a little bit difficult. Let's prove another. Let's prove these directions. Okay, so obviously that we can easily do the partial sum. For example, let's say n from 1 to m, then we get a1 up to am. Right, this obviously less or equal to 1 plus a1 up to 1 plus am. Their product. Okay, so this if this converge, then this will converge. Okay, so proof. Okay, so now these directions, we need to say that we need to say that if n from 1 to m is bounded, is convert we need to use this to bound 1 plus an from 1 to m. So what should we do? We have a formula that using calculus, we know that if a greater or equal to 0, then exponential a greater or equal to 1 plus a. Okay, so we have the product of 1 plus an from 1 to m, that's equal to exponential 1 plus an. Yeah, so it's the products n from 1 to m. This is just summation of this. No, so this, yeah, I'm stupid. So there's no one here, and then n from 1 to m. Okay, so if you have this bound, you have bound the exponential term, then you bound the product. Okay, now definition. So as infinite sum, right? So in the infinite sum, we will say something is absolute convergence. So we say the same thing. So it's like we talk about 1 plus an. So we said 1 plus an is infinite product is absolutely convergent if remember in the infinite sum we take the absolute value. So now we take the absolute value as in this 1 plus an converge. Okay, so for example, let's do some example. So 1 plus 1, 1 minus half, 1 plus 1 divided by 3, 1 minus 1 divided by 4. What's going on? So this sequence is converge. This sequence is converge. Why? Because now you can try to prove it. It's not difficult. It's not trivial. You can try to prove it's converge, but not absolute converge. Okay, you can prove that if you take all the to be plus, right? You can compute a partial sum. You can see that it's not absolute converge. Okay. I think it's not. Yeah, I think it's not important. So you can try to prove it yourself. It's not difficult. Okay. By the way, this guy will converge 1. You can try to prove by yourself. It's an interesting exercise. Okay, so theorem. So remember that compared to a theorem that if an converge, there's a result of an absolute convergence, then you prove that an converge. Okay, so what we should have is exactly the same thing. So if 1 plus an converge, then product of 1 plus an converge. Proof. Okay, how do you prove it? So to prove this is trivial, right? You remember this proof. This proof is trivial because summation an is already bounded by summation an. So if you can bound every absolute value in the product, then and in the sum, then proof is just trivial. But in this product formula, right? In this product form, we need to think a little bit. Okay. So the idea is that using COSI, so we can check that 1 plus an plus 1, 1 plus an plus 2. Let's say we do a partial sum of the 1 plus an, and then we minus 1. So this is the COSI. This is the sum, right? And one can prove that this is less or equal to 1 plus an plus 1. Because if you take absolute value, this will increase the sum, increase the product, right? So you get 1 plus an minus 1. Okay, you can check by yourself. Okay, so once we prove this, and then you also added the completeness for the complex space, then you prove that the partial sum is bounded, then it's converge. Okay, so actually we need this add the complex plane is complete. I think you need to use this. Okay, so remember this. Okay, so now we have our final results. Our final theorem. 1 plus an absolute coverage. If only if summation an coverage. Absolutely. Okay. This is almost trivial because we previously proved an greater than 0. Then you do it right. Just take the you just take the absolute value. So this is trivial. Okay, but now we have compare using this. We get this theorem. If 1 plus an converge, if summation an converge absolutely. Okay, so yeah, yes. So we should say if summation n converge absolutely, then we have this. So the proof is just using if an converge absolutely, then we have 1 plus n converge absolutely, then we prove this. Okay, so this one is also trivial. You start from here, connect here, and prove here, and prove here. Okay, so this one is, I think it's usually people use. This is the most important one. So usually, how do you, somebody give you the infinite product? What's the first way that you try to prove it's converge or not? Then you will compute its absolute partial sum. So this is the powerful, usually the powerful tool. Okay, so I think finally I need to talk about another tool which is also commonly used. Okay, so this is a theorem. This is if summation log 1 plus an converge, then product converge. Looks a little bit stupid, right? Because your sum are log a plus log b is log ab. Okay. And so this is the first one. Okay, another one is that if products 1 plus an converge, then summation log 1 plus an converge to a branch log 1 plus an. Okay. Yeah. So okay. So what this says that if I think this one is easy to understand. What this means that if the infinite product converge, then this guy will converge. But it's complex, so you need to dealing with this branch cut. So you go convert to, I think, principal branch of log of 1 plus an. Okay. Yeah, let's maybe give the proof. A proof is stupid, but so let's say summation of, let's say log 1 plus an, let's say n from 1, let's say, okay, so m go to n, and so we know that suppose Sn convert to S. Okay, then we have infinite n from 1 to infinity, 1 plus ai. Okay, so you do 1 plus ai, right? This is exactly exponential si. So if you go to n, so it's not Sn, you go to Sn, right? But this is just copy this, right? Because just take the log a plus log b equals log ab, and the exponential is continuous function. So when Sn approaches s, then it's the exponential s. Okay, so this just tell you that n from 1 to infinity, 1 plus ai will be exponential s. Okay, so now what we need to prove is what we need to show is that these guys converge. Okay, right? So this is what we need to show. What we need to show is these guys converge. Okay, and okay, so now since these guys converge, right? We already know these guys converge. So if we denote, so if this, let's call this Pn. So obviously that let's call this P. Okay, so this Pn converges to P. Okay, by infinite product. So this means that your log Pn divided by P will goes to 0, right? Because when n goes to infinity, that's Pn divided by P will be 1. Okay, so now I can write log Pn divided by P into Sn minus log P plus there is a Hn 2 pi I. Okay, so this is just stupid. This is just Sn minus log B plus Hn 2 pi. So Hn is just a number. Okay, I call it n. So this is just, I just brute force rewrite log Pn divided by B into Sn minus log P plus Hn 2 pi. It is just, I brute force do it. Okay, so which you will have log Pn divided by P minus log Pn divided by P will be log 1 plus An plus 1 plus Hn plus 1 minus Hn 2 pi I. Okay, so we know that this guy goes to 0, right? Sn goes to infinity. And so which tell me that when n goes to 0, then we have this guy goes to 0, and this guy goes to 0. Okay. By the way, we already know that 1 plus An is converge. By our assumption, right? We already know this guy converge. So as n goes to infinity, this guy will go to 0. So this guy goes 0, this guy goes 0 will require this. So these two are my assumption, and will require that Hn plus 1 goes to H minus Hn goes to 0 as n goes to infinity. Okay, so that means as n goes to infinity, Hn plus 1 will arbitrarily close to Hn. So which means that H converge. So you can, so let's say Hn goes to infinity, converge to some point H. Okay, so so now if you take n goes to infinity, then you get this left hand side 0. You get 0 goes to S minus log P. Log P is fixed log B plus H 2 pi I. Okay, so now you can solve H. Right? You know H is just log P minus S divided by this 2 pi I. Okay. So I think this proves yeah, I think this proves everything. Okay. Let's check. Check what's going on. So first we need to show if this guy converge, we need to show. I think this is we already proved because as the product of this, then we already proved it goes to exponential x. Okay. So then the rest is that if this guy converge, and as this, if this guy converge, then we want to show that this guy converge to a branch, which is exactly what we did here, right? So we converge to this branch. Okay. So final theorem is that theorem, if n goes to 1 to infinity, 1 plus An converge absolutely. So usually in order to check this, you need to in order to somebody give you this, right? You will just try to check this, right? This is the usual step. But there's a there's a more common ways that you can try to prove that if only if n from 1 to infinity log 1 plus n converge absolutely. Okay, so this is the proof used the same technique as previous what we did. So let me just skip. You can try to prove by yourself. Okay, so I think this is the my introduction for this infinite products. I guess the most important one probably is this, right? So you convert absolutely, this can convert actually only if convert absolutely. So and if summation convert absolutely, then the infinite product converge. So this I think this one is much important, and this one probably not so important. And this one usually also people also use. Yeah, I think in order proving technique, I guess probably this one is the proving technique. Also, this one for every area greater than 0, then this one is also commonly used. Okay, so see you guys next videos.